The DNA of matter. Differentiation of protons, neutrons, and electrons by thread folding in Spinon structure. This paper proposes that protons, neutrons, and electrons are not identical particles, but are structurally distinct based on the configuration of underlying threads and spinons. According to the Threads and Spinons Theory, these particles possess a unique structural identity based on how threads are folded and spinons are stacked. Just as DNA provides the blueprint for biological organisms, threads and spinons serve as the DNA of matter, encoding unique properties into each particle. This paper explores this new view's theoretical basis, implications, and possible experimental predictions. Introduction. Standard quantum physics considers protons, neutrons, and electrons to be indistinguishable among their respective kinds. However, this simplification may overlook finer structural variations. The Threads and Spinons theory introduces a structural foundation where each subatomic particle's characteristics emerge from its unique configuration of folded threads and spinon stacks. This framework offers a deeper explanation for particle individuality, isotopic diversity, and subatomic anomalies. Core hypothesis: particles as structured entities. Unlike point-like particles in standard models, the Threads and Spinons theory treats particles as spatial structures. Threads, one-dimensional constructs that fold into complex geometries. Spinons, rotating units that stack upon threads to create energetic profiles. Each particle's identity stems from the following: the number of spinons in the stack, the orientation and pattern of thread folding. The distances between spinon stacks influence interaction range, energy state, and internal coherence. These structures create the energy configuration. These principles apply not only to protons but also to neutrons and electrons. Each of these particles may differ from others of their kind in subtle yet real ways based on the variations in thread folding, spinon arrangement, and spatial distribution of spinon stacks. Thus, the theory extends the idea of structural individuality to all core components of matter. Quark variability and emergence. In this framework, quarks are not fundamental particles, but emergent patterns arising from particular thread and spinon arrangements. Consequently, each proton or neutron may feature slightly different quark configurations, offering a physical mechanism for isotopic variance, binding energy differences, and subtle nuclear behavior. This logic also extends to electrons. Their electromagnetic behavior may reflect the internal configuration of spinon stacks, thread orientation, and the spacing between spinon clusters. These factors result in measurable differences in magnetic moment, interaction patterns, or radiation emission under specific conditions. Moreover, the formation of new elements over time can be seen as a consequence of continuous structural evolution within protons, neutrons, and electrons. As threads refold and spinons reconfigure, including changes in the spacing of stacks, atomic nuclei may transform, leading to the natural emergence of novel elemental structures in the universe. Threads and spinons as the DNA of matter. This structural uniqueness positions threads and spinons as the equivalent of DNA for matter. Just as DNA encodes biological identity, thread folding and spinon stacking encode a particle's physical identity. This analogy deepens the theory's implications. Matter is not composed of identical building blocks, but of structurally unique units. Identity in matter stems from informational patterns, not merely numerical count. Even electrons, long considered perfect clones, carry their structural signatures. The spacing between spinon stacks adds another layer of information encoding. The genesis of new elements is directly tied to the transformation of internal thread spinon structures. Experimental implications and predictive power. This model predicts measurable anomalies between particles thought to be identical, e.g., slight mass or decay variation. Possible detection of structural differences using ultra-sensitive spectroscopy or particle collision data. Correlation between subtle structural variations and quantum noise. Detection of variation in electron behavior under precise measurement conditions, including slight differences in energy levels, magnetic properties, or emission spectra. However, Our current instruments and experimental techniques may not yet be capable of resolving these microscopic differences. The structural variations proposed by this theory may lie below the resolution of existing technology, which treats particle identity as idealized uniformity. Check out the Threads and Spinons light theory books on Amazon, links in the description.